Thanks. Good morning. It's still morning. I think you are a bit tired after this week of marathon. Thanks for the invitation, Orkun, also the other organizers. I saw the title of the talk is Quantum Foundations, what a big, terrible title. Of course, this is a very deep subject, and we have many problems about the foundations of quantum mechanics. We touch some of them. But I just remembered when Orkun mentioned this possible title, this figure. You know this, right? This is from my first quantum mechanics text, Stephen Gastrovich, first chapter. This was 40 years ago. It was my textbook. And there was this picture towards the end. This is about one of the debates between Einstein and Bohr. They discussed many things. And most of them were raised by Einstein. And he was trying to cheat a sort of uncertainty principle. Ways to overcome delta P, delta X. Ways to overcome delta E, delta T. This is about the second version. I don't know if you discussed this energy time uncertainty in the first days of this week. This was all about computation. It is about the computation. It is the most important thing about quantum. And this was one of the first problems. You might know the argument here. The idea by Einstein was that, look, I found a way to overcome this delta E, delta T uncertainty. Think of a particle, say a photon inside this box, okay? And using this instrument, I can just control this opening. So I can release the photon or I can keep it inside. In this way, I can measure the time in any, it is my view, with any precision. And at the same time, looking at the scale, I can measure its energy. After many examples, for the first time, Bohr was shocked. He found some way, how can it be? But the day after, he found a solution by using the theory developed by Einstein himself, which was general relativity. Because when this shifts, according to general relativity, equals principle, there will be an additional uncertainty. Time runs different at different speeds, rates. When you are down, it runs slower. Okay, so that is why our feet remain younger in comparison to our head. And this is how he solved the problem. So this is about delta E, delta T. And when this title was mentioned, Quantum Foundations, I remembered one of the YouTube videos. I watched YouTube videos a lot. My late. I think you know him. He was my hero, but still is. But he was, he is known in condensed matter physics, but he also did many works on functions of quantum mechanics. And this is a relatively recent video where he warns the young generations. Don't spend too much time about this quantum foundations, some basic problems. Do not, put all your time in this direction. Yes, maybe this is a good suggestion, but it was the end of 80s or beginning of 90s. I remember that he was also saying that, oh, you see, we can never observe quantum effects at large scales. For instance, superconducting ring, although superconductivity is a result of quantum mechanics, PCS theory. When we go to larger scales, because of interactions that we cannot prevent, interactions with the outer world, we cannot see quantum effects. But I was still in big and it was the beginning of 90s. People observed for the first time superposition of currents in superconducting rings circling in both directions. And today, if we have quantum annealers and prototypes of quantum computers, because we have microscopic superpositions. Right. As of today, no one knows where quantum mechanics will stop. We don't know any border. There is no known border between classical and quantum in that sense. On the other hand, by the way, he has also very nice lectures on time-symmetric quantum mechanics, which I will talk about towards the end of my talk. And the works in so-called time-symmetric quantum mechanics, or weak values, weak measurements, were criticized by many colleagues by saying that these are not real measurements. And yes, maybe as a terminology, they are not of this type, but it was Tony Leggett again, who pinpointed the importance of this actually now 60 years old subject, because it is becoming more and more important in experimental physics. Well, you know him as well. Basically, he is saying that we know how quantum mechanics works, we know the math, but we don't know the mechanism still after a century. Okay? And this has been a motto for many physicists, especially students, because you started by reading the lectures on physics by Feynman, and it was 60s that one of the first critics raised by is the Aharonov-Bomb effect. In fact, at that time, again, 60s, if you listen to him, some of the recent videos of Aharonov, Bohm was the only one who were working on fundamentals of quantum mechanics. Okay. Today, because of this recent developments in quantum technologies, we working in fundamental sciences have some chance to retouch or rethink about these problems. Okay, so for today, I still wanted to be a bit more modest, and rather than foundations, let's talk about a few problems about the fundamentals of quantum mechanics. You already spent 1 or 2 days, I don't know, at the beginning of this week, but I've been teaching quantum mechanics for almost 4 years, I don't know. And I see some colleagues here who are teaching or who will be teaching in near future quantum mechanics. There are some points that I think is still missing in many or almost sometimes textbooks, but these are important. As Nogunaja raised, for instance, the point when I mentioned this uncertainty principle, the first one is energy time uncertainty. It is always there. It was there between Einstein and Bohr, and last year when they announced this Nobel Prize, they said this up-to-second experiments, they are violating the uncertainty principle. No, nothing was done. If there is a law, if there's a principle, because it is there. Okay, the experiment, they have been verified experimental. But here is the question. Say, take a quantum computer, and this question was discussed very recently. I think 1998, or 20 years is recent. Okay, so this is not something that people discussed at the beginning of quantum mechanics. Here's the question. Basically, when we have delta P delta X about H, necessarily we have delta E delta T H again, but the meaning are very different because we don't have time is not a in the sense that delta P delta X like a result of measurement, right? We don't have time operator, etc. But still, you can write such a thing. Now, the practical question raised 20 years ago was the following. There was the Shor's algorithm, machines, everything. How fast can we flip a qubit? Say we are in say 0. How fast can we make it 1? Right? Is there a limit coming from the foundations of quantum mechanics? Okay. No one asked this question before in such a clear way. After 4, 60 years. Well, so this is our initial state. You know, this in time this evolves, the CNs become CNs times phases. So let us evaluate this correlation, the over overlap between initial state and final state, and let us require that this is 0. At time equals 0, when t is 0, this is 1. Then we wait. When does it become 0? For the first one. So it means that it flipped. So it was a qubit in this direction, now in this direction. Up, down, 0, 1, etc. Okay? The usual answer is this one. If you are a typical quantum mechanics student, you read the book, delta E, delta T, so uncertainty requires that much time. But it turns out that the answer is not that simple. A bit complicated, but still simple. There is a simple relation between cosine and sine, inequality. You can easily check. I don't know how they formed Marcus and Levitin, but you can check this relation. So if you go to the previous expression, you can write this relation between real and imaginary part of C. And we want C to be 0. C is 0 if it's real and imaginary parts are 0. Raise them, you find this relation. What is the difference between the two? H bar, H, 4, and E. Instead of delta E, we have E. And they showed in this very short paper that there are examples where this is the bound for T perpendicular, and there are examples where the other one is perpendicular. So in practice, if you want to use energy time uncertainty, you should check both. Evaluate delta E and evaluate mean energy, okay? And compare which one gives which bound. Whichever one is stronger, it wins, okay? This is number one. The other one is about uncertainty principle. This is proven even in undergraduate books, okay, in Kassovich or in Sakurai, everywhere. And I don't know any proof in textbooks other than this. Oh, we cannot read it, unfortunately. There are Schwarzschild quotes on these t-shirts. And Schwarzschild is, by the way, black in German, right? So this was a joke. Anyway, on their t-shirts, it is written U magnitude times V more than or equal to inner product. So this is something like generalization of cosine is less than or equal to 1, okay? In Hilbert space. But there is a, record proof, the simplest ever proof for this one. If you use this upper on the left magic formula, I don't know whether you have seen this formula in any book or quantum mechanics courses, but it is true. If you apply any operator, Hermitian operator, on a state vector, you obtain the same vector multiplied by the mean value and delta A times something perpendicular to this. Something perpendicular. That is it. Okay? It is easy. I asked this many times in many midterms and also one of the qualifying exams in sub-100. They showed it. Anyway, so given this dual correspondence, we have this. Of course, this is true for any operator, dual correspondence, this. Then multiply them in this way. İçler dışlar çarpımı, okay? Subtract the first row from the second. You obtain this one, which is the proof of uncertainty principle. No Schwarzschild equality, nothing. Two things. I know that we are expected to give some homeworks or questions. Question one then. This is very simple because this part is less than or equal to 1. That is why we obtain inequality. The previous one, the one that you all know, okay? But when you discuss uncertainty principle in quantum mechanics, it is there in, for instance, in Shankar, in Sakurai as well. If you ask, when do we have equality, there are two conditions. One, there should be equality coming from Schwarz inequality, which means that the two vectors should be parallel. There is a second condition, and the commutator of A and B satisfies some condition, okay? But here, equality is there only if we have this one. Okay, how can it be that two conditions become one condition? This is the first question. The second question is this one. In 2 dimensions, we have 2 orthogonal vectors only. We cannot have 3 orthonormal vectors, okay? So, if we have psi, then psi perp is orthogonal to psi. There can be only one such a vector. Then this must be 0. Then all operators in 2 dimensions for a cubic must commute. You know, this is not true, but well, okay. So we can talk about them if you want at the end, after the talk. Well, another thing related to this is the proof of Wigner theorem. Wigner theorem says that if you require some transformation to preserve moduli of inner products, then this transformation must be either unitary or identity. In quantum computation information, most of them are unitary transformations, all the gates. But when you discuss time reversal operators, you are here. Anyway, we use both of them. These are much more common. But they are either this one or that. Okay? This is called as Wigner's theorem, coming from the early use of quantum mechanics. If you look at again the proofs, say the red book, John Sakurai, he says, proof of this is a bit complicated. Please refer to the book by Gottfried. You open Gottfried. It says, he uses some footnotes, he makes a proof using arguments by Wigner. Okay? And if you look at the basis of this proof, it uses the fact that the magnitude of this inner product or scalar product is physical. What we observe in real life is not the complex numbers or phases, but the magnitude of these matrix elements. In transition probabilities or probabilities themselves, they are all of this sort in quantum mechanics. But it's a long proof. However, we can prove this Wigner's theorem in one line. If we know that it is not only magnitude of scalar products, but also this kind of triple products are physical. After 1984, we started to call that kind of products as, or the phase of this as Berry's phase, due to Michael Berry. But it was there. This kind of products were already used by Bergman in 60s to refine the proof of Wigner's theorem. But if you take this as an axiom or beginning point, look, if I take A, B, B, C, C, A, that kind of triple products, these triple products are very special in the sense that, yes, you can multiply any qubit state by a phase, right? They are defined up to a phase. That is why we talk about projective spaces. Rather than points, we have rays, lines. But if you do a transformation, look at this one, A, bra, A cat, B, bra, B cat, C, bra, C cat. They come as couples. So if you multiply by a phase, the other one is multiplied by the conjugate, so nothing changes. So these are invariant under transformations, under any transformation, okay? And if you look at this magnitude is fixed, and not only the magnitude, but this phase is fixed. And it is known in math and vector algebra that they correspond to so-called geometric phase. In physics, we call them as Berry's phase, Berry's angle, etc. Now, if we say that A, B, B, C, C, A type Bargman invariants are physical, then after transformation, this must be the case. So if this is unitary, A, B is same as this one, this is same as this one, this is same as this one. If it's anti-unitary, these are stars, so angle goes it's minus. But if some of them are unitary, some of them are star, and some of them remain same, angles are not preserved. So if we require that angle should be preserved, which is physical, then necessarily Wigner theorem is there. They should be either unitary or anti-unitary. One more thing, from time to time, you see some news about magnetic monopoles. We don't have magnetic charge in classical physics. We didn't see them in quantum mechanics either. And if you look at Maxwell's equations, there was nothing that prevents us to put a magnetic charge there. We can write, we can obtain the equations in the most general way. But, and also there are some recent news. You might follow, for instance, the work by Meta that came last year or so, and they obtained some, magnetic monopole-like composite particles. So people are working on that, even if not the fundamental magnetic monopole things. Its analogs are still among our problems that we are studying in laboratories. Anyway, again, open the books, okay? This includes not only Sakurai, but also Jackson, okay? They say that magnetic charge is quantized. Yes? You know, or you remember the discussion. You define a vector field A, where curl A is magnetic field. Then you use some consistency condition, you match that, okay? Or you can use, if you want, not two pieces of vector field, but a whole sphere, but you need to have some string. These are called as Dirac strings, okay? And you find this condition due to Dirac. Magnetic charge times electric charge is an integer divided by 2. And this is what you find all the books, in all the books. But it has been already shown at early days by Schillinger that this can be refined. It is not integer over 2, but it is integer. So these are missing. There shouldn't be these values, okay? But all of these proofs are rather complicated, this vector fields, matching things. But there is a very simple, not very, but simple, very simple proof. Again, it has been subject to some exams. Here is the question. Let us assume that we have a magnetic charge, okay? And then it will create such a field, magnetic field. Then, question. What are the angular momentum or rotation operators in the presence of magnetic monopole or magnetic charge? Well, you know, even from maybe high school, like these freshman physics, first trial is this one, angular momentum is R cross T. But no one uses this in quantum mechanics or even classical electromagnetism because it is not eigenvalue. The next thing that we can think of is to put this canonical momentum and this physical momentum, they are different, you know. But if you do so, you can easily check that they do not satisfy these relations satisfied by X, Y, Z gates. Okay, these are examples, pole operators. In general, they are J's, they do not satisfy. The way the correct solution is this one. And R cross T, if you consider this one, R dot J, our here, vector product is orthogonal to this one, so R dot J is what? It is EG, and this is 1. You can easily find the eigenvalues of this. These are 0, +1, -1, etc. And you obtain this result at once. Okay? I think there was fifth one. Yeah, this is important. Sometimes people ask the following question. What are the differences, or what is the basic difference between quantum probabilities and classical probabilities? Actually, we had a whole week on theory of quantum, the quantum probability theory in Bilimler Köyü this year in Foça. Kolmogorov axioms are very simple. Maybe you even read or think about them because they say that probabilities are described by numbers between 0 and 1. And for a given set of events, the probabilities add up to 1. Okay. And also, if we take the whole set, event set, probabilities. But the exclusivity or so-called local orthogonality principle says an additional thing. If we have events excluding each other. Let's say we have a qubit, say 0, qubit 1. Or we have a qubit in state 1, then in state 0. These are excluding, mutually excluding events. If you have binary sums of such probabilities, and if we take any two in the set, and we see that any other pair has at least one excluding event, principle says that this sum is also less than. So it is long inverse, but equations are much simpler. Look at this one. For instance, here we have A2 and A2 common, right? But here in the first one, A2 is plus, in the second one, minus. So they exclude each other. Look at the second and third. We have A3. In the first one, it is minus. In the second one, it's plus. They exclude. The first one and the last one, A1s, are common, but they are plus. They exclude. Then this principle says that this sum is less than or equal to 1. Without this principle, if we go using Kolmogor's axioms, we can write this because here we have this and this. Here we have this and this. Here we have this and this. Sum them. We obtain 2 times S on the left. On the right, we have 3. So standard Kolmogorov axiom says that this is less than or equal to 3 over 2. But in quantum mechanics, we have less than or equal to 1. So we have an additional constraint. In fact, if you use this constraint, you can derive quantum mechanics, the predictions. And this was this is from my last encounter with Professor Alexander Kuliachko in Bilkent University. I was giving a colloquium, a talk on by using this principle. This discussion is due to Kaderio. You can derive even the violation of KCBS inequality. KCBS inequality says that 1, 2, 2, 3, 3, 4, 4, 5, 5, 1, like sum, where A can be plus 1, minus 1, cannot be less than minus 3. But in quantum mechanics, we know that Kryachko, John, Vinjol, and Shimorsky showed that this can be as small as minus 3.94. Without using Hilbert space, no qubits, no entanglement, nothing. Just use this kind of probability relations. For instance, we have here, say, 2 pentagrams, 2 independent events. Okay, there's no entanglement between the 2. We write the probability to obtain, say, plus here and plus here as a product because they are independent. And we assume that if there is a violation of KCBS inequality, this must be universal. This must be the same maximum violation for purple and yellow pentagrams. You can obtain the square of this quantity, which is 5, then you prove it. You can do the same thing for band inequalities. Okay, so this is so fundamental. Please keep E principle in your mind. Adi Cabello was our main speaker some years ago for COVID in Ankara. He made many calculations. He used this relation to prove some relations, but still, especially in some applications, if you are anyone working on, probability theory, you can find, I'm sure, some interesting applications. Okay. So there are many other things. Just to name, if there's any title that is interesting for you, we can discuss later. For instance, this linear Schrödinger equation. When you discuss relativistic quantum mechanics, the first thing you see is Dirac's equation. Dirac's equation was something that people discussed in quantum field theory in 1980s when I was in Middle State University. So it was a subject of high energy physics, quantum field theory. Then there came 20s, the 2000s, and they had this graphene. All condensed matter physicists started to learn about Majorana, Fermions, Dirac's equation, etc. But I think none of us know about this fact that when you look at Dirac's equation, you obtain this electrons G factor 2. Oh, you see, this was one of the first achievements of Dirac's equation. In Schrödinger's equations, you don't have this relation. It is one. With Pauli substitution, maybe you can show two, but it is artificial. But in Dirac's, it was two. But if you linearize Schrödinger's equation, you obtain the same thing. So G equals 2 comes from linearity, not relativity. The second thing is very related to this one. Quaternion Dirac's equation. When you write Einstein's relation, this E squared is m squared C2 plus P squared C2 squared, you obtain Dirac's equation, but you need some objects satisfying some relations that cannot be achieved by numbers. So that's why Dirac said that, oh, I cannot do these numbers, not 2 by 2 matrices. I need 4 by 4 matrices and 4-dimensional vectors. This is how he developed Dirac's equation. But the same thing can be done by using quaternions. This was known very early at Dirac's time. And one of the earliest contributions in this field was a PhD thesis in physics by Zafer. So you can do all these things by using just quaternions, okay? Some things about this trace row cube formula. This is the most important one, unfortunately, in yellow. You might know the story. Ceyhun Hoca was here, right? Ceyhun Hoca, Salih Hoca were in our PhD thesis jury by Solomon Samuel, my last PhD student in Sabancı University. And at one point, after he finished his presentation, Ceyhun said, Solomon, in your thesis, maybe this most important thing is for me to see that this simple formula, density matrix cube trace equals 1. I think you know that this is the necessary and sufficient condition for rho to be a pure state. No one noticed this. This was in a footnote in a paper, in some other place, etc. But then it turned out to be the most important formula in so-called Zornier's conjecture discussions in quantum information theory. And then Ceyhun said this, he appreciated this. And then, after Solomon put his article on archive, we received some very good comments from the experts or founders of the field. And one of them was Magnus Appleby. He said, this formula is very important, something like this. I say the same thing, Ceyhun just said the same thing. So it was a sort of, appreciation of the simplicity. Keep in mind, the proof is very simple. You don't need to have rho squared equals rho. This is a very difficult equation. This is about traces, okay? If trace rho cube is 1, this is enough. And we have Majorana stars. We can denote not only qubits, but qubits by using a single block sphere, but more stars on it. And tunneling, this is some old story. We have many misconceptions about tunneling. The basic thing is that still there is something that we can call as tunneling, but many people think that, I have a barrier and I have a particle here. No, you cannot say this. If you have a barrier, you cannot talk about a particle on this side. If you are here, then you need to have a wave packet which includes all the states, energies, even about this barrier. You can have your mean energy less than the height of the barrier, but you cannot have a particle on the right and at the same time energy, the maximum energy below the barrier. Okay, so this is why let's answer this. It's so obvious. It has been discussed by many colleagues, especially by Weidman. Well, we would talk about foundations, or I don't know what to say about foundations, but maybe one important thing you see when you switch from one version of office to other one, this was fitting into the box. Okay, so you see, one point we should, I think, appreciate in a clear way. This is the subject of 2002 Nobel Prize, right? Very important. Many quantum applications, especially quantum key distribution, many other things depend on this. They use bell tests, etc. Here, basically, we have this is a version of Belling's fancy for the CHS H inequality. In fact, we should put in bond, certainly, if you are wrong. But here, the point is that if we assume that A next to B and A next to B prime are the same, this number cannot be less than -2 more than +2, right? But in quantum mechanics, it can be as big as 2 times square root 2, as small as 2 times -2. So the result, the lesson is that A here is not same as when it's next to B or next to B prime. This is correlation in space. And similarly, this was not known, shown, maybe Bell didn't think, maybe he thought about, but he couldn't solve, we don't know. But KCBS inequality shows the same thing in time domain, if you want. If we assume here that A, after this, I can measure B or E, are the same, this cannot be less than -3, you know, because we have 5 numbers. This can be plus minus 1, plus minus 1, plus minus 1, plus minus 1, plus minus 1. We take the binary products, we want to make this as small as possible, so we try to make them opposite signs, right? If this is plus, minus, plus, minus, plus, or both are plus, so you can never make this less than -3. But in quantum mechanics, it can be as small as this one, okay? So it's also valid. Then here's the question. When we talk about foundations of quantum mechanics, I think the most important problem is the measurement problem. By measurement problem, we're not talking about the random time evolution. We have a random result, right? We have possible outcomes. It can be 0 or 1 or eigenstates of operator A. One of them is randomly, produced. This is some issue. But even in classical mechanics, we can introduce some randomness. For instance, we can mimic, we can simulate a single qubit by using a classical pseudo-random number. You cannot distinguish them by any means, but if you have a qubit, there are ways that you can beat classical random numbers. Anyway, but there is another one, much deeper question, and this takes us from physics to some other things. And this maybe the most important problem is unfortunately not appreciated by all physicists. It's the following problem. Here, okay, these calculations are easy. Even sometimes in summer high school, in Sabancı University, some students can do this. I saw it. But here, after we do an A measurement, say we are going to do a Bell experiment, we can decide between B and B prime. We are here. Or we are going to do the KCBS experiment. After A, we can measure B or E. We are not now, but that will be future. Someone here will decide, say, I understand Bob. Bob will decide between B and B prime, and the result here will change. Or depends, not change, but it depends. Similarly, after Alice, say, Bob and Alice will do some measurement. Someone will choose between B and B. So there is this problem of choosing between the two. Say, after A, whether we are going to measure B or E, when we are measuring A, here someone there will measure B or B prime. So contextuality is directly related to choosing between, unfortunately, I have some shifts, but I think you can correct that in your mind. So the first one was this. Contextuality means there is no reality independent of the choice of measure. So we cannot assign a value for A without saying whether we are measuring B prime or AE. And some observer will decide this. And this we call as free will. This we call as consciousness. That is why some of the names you saw them, for instance, Yakir Arno, and before him, David Bohm, he was also spent some time on this issue. This is completely open question, and you can see many, works about this. What is consciousness? How to define this? Some other. Anyway, so deciding what to measure means consciousness. So this should be on one line. So this is on the left, this is on the right, and there's an arrow. Okay. So this is about the most maybe fundamental question. Something, you see, let us find something in between warnings by Tony Leggett, always important for me because he was my first, teacher. By the way, he came to Turkey. I was in my, short military service. Short means 1.5 years, and I was again in Ankara. Before going to the service, we already had some plan because I didn't know that I had to go. There was a conference on superconducting. So Leggett came to Ankara, weekend, before the Nobel Prize was almost, 20 or no, sorry, 25, almost 30 years ago, okay? So he is a very good teacher. Now, just read all the books also, his lectures are now very good. Anyway, but he, in spite of his warnings on fundamental, don't worry about all fundamentals of quantum mechanics, he has some interest on time-symmetric quantum. You see, when you talk about or ask someone, physicist, time in quantum mechanics, the standard time says time is a parameter in quantum mechanics. Yes, this is, everybody knows. This is true for Schrödinger's equation. It's so simple. It is some differential equation. Yes, mathematically not very simple maybe, but it is clear, it's a parameter. What we are talking about is the measurement problem. All problems are here. Here, you just take t to minus t, the wave function star, which is clear that there is an I in Schrödinger's equation, time reversal is obvious. But here, when you have psi, you have a measurement, everything lost. Projective measurements collapse. What happened? It was Aharonov Bergman levels, 64. But before, in 1953, Stoji Watanabe discussed. These are independent works, and they are more general than quantum mechanics. There's about probability theory. Is it possible to make measurements also time-symmetric? They showed that it's possible. Not very difficult. Basically, you do a measurement. You prepare some state, you do a measurement. Then you can so-called garbled states. You can show that you cannot do this with a single operation, but you need two operations, rounded operations. And after that, you obtain a density matrix, which is completely diagonal. 1 over d, 1 over d, 1 over d, 1 over d. No information, maximally mixed. Okay? This is not difficult, but you can show that commerce is also true. Say we have some initial state, we can garble them, and do a measurement in between, and the final state is selected. Well, so the basic point before coming to this is something disturbing for everybody. This is nice. This is deterministic. Wave function is evolving in time. Cubic is evolving in time. Whatever we are doing. But when we do a measurement, we have a jump and this jump. First jump, discontinuous. Second, there is randomness. Okay. But what we observe in laboratory, you also saw some examples today, for instance, for error correction as well, right? We have these mean values. We observe mean values. This is physics. I don't have a tree picture here, but on the left we have a tree. Okay. On the right we have math, Hilbert space. Substitute this cat parameter. This is 1 according to Feynman. This is the most basic important formula in quantum mechanics. Put it there. You obtain this one. This is an eigenstate. This is A. This is a final result. This is perhaps you also refreshed your memories on Monday, but this is how we interpret in quantum mechanics. This is probability. This is the value, right? How much you grade you obtain from one exam, and this is the rate of the exam. Of course, it gives the mean value, right? Eigenvalue value times probability plus sum, all of them, you get the mean value. I don't know whether you were born in a quantum mechanics lecture when we were sitting in class and did the following. Professor is putting this A there, cat, bra. Let me put B. Same thing. This is also 1. If you repeat the same calculation, it's a side B. We want to obtain some, B psi modulus square. So let us divide by B psi and multiply by B psi. We obtain this. Okay? Do not try to memorize because I wrote the same thing in the next page. On the left, this was the original formula. This was probability, and this was eigenvalue. These are supposed to be fixed. So, on the right, we get the same thing. Because according to Born's rule, this is probability. But the numbers here are strange. They're not eigenvalues of A. Do we have a physical meaning? First, look. Here, the point is that there's an axiom. When you do an A measurement, you obtain one of the eigenstates of A. Who says so? Someone says so. Someone said so, 1920s. But 40 years later, after AB 11, in 80s, 60 years later, Arnold, Albert, and Weidmann raised an argument. Maybe when we do a measurement, if it is not a very strong projective measurement, if we do this weekly, if our system and measurement device interact weekly, we can still do some collapse or disturbance, but the final state is not necessarily A, but some other thing, B. So this was the idea. This was a purely theoretical idea in 1980s. And here, be careful. Normally, we have eigenvalues, real numbers for Hermitian operators or matrices, right? There is a minimum one, there is a maximum one, we obtain numbers in between. But here, this thing can be anything. It can be complex. It can go to infinity. Okay? It can be anything. But still there. It is a complex part, but when you evaluate the mean value, complex parts cancel. There are as many minuses as there are pluses, so they cancel each other. You obtain at the end the real thing. Okay? So this is the resource. I think many people, many historians, not many, all, they said he was a very strong man. He determined the direction of quantum mechanics by interpretation, Born's rule, Born's interpretation. Also, this projective measurement, they were all coming from Born. What now they discussed 30 years later, this generalized time reverse states. If you have an interest in classical statistical mechanics, for instance, there's so-called H theorem. From a very simple argument, from a phase space argument, we obtain, we can convince ourselves about the entropy, or we can obtain, say Maxwell's the velocity distribution, things like that. So he was also discussing that kind of things in 1955. But then they came on similar results obtained by ABL. The 1988 study, Arno, Albert, and Weidmann, was important because they developed for the first time something that we can measure in principle in our. And last COVID meeting again on this campus, we were told from the experimental group to get kind of weak measurements. Well, so the point is that we have now, if you look at the expression that we had a psi, we had b, instead of b, let us use phi. So the idea is then we can increase our power, if you want, by not only preparing a state and doing a measurement, but also after measurement by selecting hoşumuza gidenleri seçmek. Okay, we choose some of them, we discard others. In this way, and these phis are not necessarily what the eigenstates of our what we are measuring. Okay. okay? We can do many funny things. For instance, you might know this example, this 3-box paradox. You can prepare a state, and as a particle is inside this or this box. We have 3 boxes. As a plus b plus c divided by square root 3. Final is a plus b minus c divided by square root 3. You can show that each time you look at A, the particle is there. Each time you look at B, the particle is there. This is something that we cannot obtain in a usual quantum as preselection case, because we would have 1/3 probability, 1/3. Okay? So, but if we use post-selection as well, we can do this kind of measurements. We can, in double slit experiments, we can know not only which slit the particle passed through, but also whether it is a dark or bright region. And these are done, by the way. These are all now in laboratories. Well, one last thing is about this. We said fundamental sum as an application. Again, as our magic formula. Okay. Operator acting on state vector is the mean value of the operator times state vector plus uncertainty or variance. Okay, variance times something probability. Now let us evaluate weak value. You can easily check now that weak value is a real part like this and an imaginary part like this. Okay, and this is something. This also explains why we have these complex parts of weak values. They cancel each other at the end, but their form is like this. You can watch videos by Arno as well. He has many lectures, and he likes to explain this kind of measures on the board. And in one of his talks, I remember times, he was saying that, look, if you do a big measurement, say you want to measure the position of a particle, we have complex part and imaginary part. It's clear from the argument that a mean value is the mean value of x. But still, this is x, this is I times y. This y should have some physical meaning. And in this video, he says that if you are measuring position of the particle, yes, this point points the position, but this y is the momentum of the point. There is a way to prove this because y corresponds to conjugate variable. What is conjugate to position? It's momentum, because we have delta x, delta p is h bar. Okay, so if you take any other thing in your quantum computer or processor, you can find a conjugate variable. It's a Fourier transform of the original one if you want. This is what you obtain. But if you ask the following question, let us write this complex number, not in Cartesian form x plus iy, but in polar coordinates, r times e to the power I theta. What happens? Does theta have a meaning? You see from the title it has a meaning. It corresponds to the area space. This was some question that I had an interest some years ago, but it is easy to show. So this is weak value, this definition. Let us assume that this A is a projector, which is a rank 1 times operator. Okay? So we check, for instance, if the particle is here. We check if spin is up. We check if our qubit is 0. Okay? Put it here. The equations explain themselves, right? Multiply by this, divide by this. And I think you completed the calculation. The answer is this. So this is what? Pi times omega, omega times psi, psi times phi. That's a triple product, Barman invariant that we mentioned at the very beginning. You remember we had A, B, B, C, C, A. So this has a certain magnitude, and the phase is called as Berry's phase or geometric phase. So if you consider any, say, this is our initial state, preselection, post-selection, what we are measuring, the 3 vectors define an angle in Hilbert space, and this is invariant under any transformation, transformations. This angle does not change. The phase of this weak value has also a meaning, physical meaning. And I think this formula is very interesting because it's that we had in last 80s, we had two important works. 1984, Michael Berry discussed or just brought the International Physics Committee this Berry's phase. And 88, weak values. It seems that these two are closely connected for certain kind of measurements. I think we can spend some time for questions, and also time is important. We had a 1 hour. Let's finish by, again, Bohn's rule. We have Bohn's rule if we have an initial state and a final state according to this formula, modulus square of this product. This is a purely mathematical expression, gives us the probability. Okay. But there is also so-called Bohn's conjecture. They are not the same. Please try to fit this into box. But here, what he says is that it is not possible to predict the outcomes of quantum measurements. This is the basic. This is the all quantum random generators, right? And as far as we know, this is the only random thing that we know in the universe, or finally. These numbers are not like pseudo random numbers. They should be real random numbers as far as we know. There are many, of course, other alternative discussions. There's so-called superdeterminism, which say that it also solves consciousness or free will things. It says that there's no consciousness, there's no free will. What I will do tomorrow is fixed. What I will choose is something that I think that I am choosing, but it's not so. Things like that. In philosophy, everything is possible. We should discuss all of them. But at least these machines are working. We are paying, we are using in their life for security. Okay, random is there, but this is still called as a conjecture. Okay? The other one's rule, it works, but this is something we should think about. I think I will stop here. I spent exactly 1 hour. If you have any question, I can try to answer.
Do you have any questions? No? We have ask a question. What exactly constitutes, deep measurement or regular measurement? I understand the collapse, of the wave function to one of the eigenstates, the real sense of measurement. But if you look at photon, for instance, traveling through all these optical elements, there are beam splitters, ray elements, the original photon is not the same photon, actually, if you look at it, that you measure in the detector.
Yes.
Because
but the state is the same, yes.
But the state is the same. I mean, it goes through all these interactions with the dipoles, in the because that's how you induce, polarization and things like that. It's basically the interaction between the photon and the dipoles, these elements. And all these interactions does not cause any collapse of the state. You still measure the same quantum state, as you induce initially.
I see. You see, your question is so basic. Actually, before any big measurement theory or so, let's ask the following question. Say we have a bifurcated material, something, and we send a photon. We think that we split them. When a photon enters a medium, a crystal, what we know, according to current understanding, it is absorbed and it's absorbed and it is no more. It is not a particle that we think of in classical. It is a state that is transferred. Maybe an easier thing to visualize because the solid state is more complicated. Is Steiner experiment, right? We send the spin, image to magnetic moment, they are related to each other. So we have magnetic gradient. Gradient splits the two states. So we have upspin and downspin. The idea, 88 paper, was we use a gradient which is not so strong. So instead of splitting them, they overlap, something like this. Still we have some information, this was the idea. But I have a third, I think much simplest for me example, magnets. You know, if you divide a magnet into smaller pieces, you obtain smaller magnets, and this is written and told everywhere. It goes to tilt the atom, and it goes sometimes the nucleus or electron in the orbit. Okay, but they both spin one half. Right, states. And there is no explanation for spin. No classical physics theory can explain spin one half. And so it's a quantum state. We observe it. There are magnets everywhere. They don't collapse. No, we are doing big measure. We have Avogadro number many magnetic atoms. They are there. We are getting this information. We know that they point in this direction, but we are not collapsing. We can collapse if we do a strong magnetic field or if we heat something, we can collapse. But so we are doing this in our daily life actually. Also, I think we can explain this presence of crystals as well. We saw that we obtain PXY orbitals, or we know that this molecule would have this structure. They do not collapse. In quantum mechanics, we teach something. In chemistry or quantum chemistry, we do something, and they look in conflict, but they are not, because we are not teaching big machines. I think so.
I mean, it seems it's all about information, you know, I mean,
It's
unless you
Yeah,
give
you
some
are-
information about the state, you know, it doesn't matter.
Yeah.
You just preserve the original.
Exactly. In your example, it is information, and it also says that I think there are no photons. There's a single photon. In the sense that photon is a collective name for an elementary particle. It is created here, absorbed, emitted, etc. So this state is information is transferred. You cannot paint the photon, and you cannot say that this is my photon going to this beam splitter or so. This is not the case. For photon, it is easier maybe to think, but for electron, in fact, the same.
Single field for the.
So what is essential is a quantum field.